Welcome aboard, where aviation concepts become simple. From instruments to aerodynamics, we make exam prep clear and cockpit learning faster. This is StudyKwik Aviation.
Welcome to StudyKwik. In this video, we are discussing air temperature measurement in aircraft. Accurate and reliable measurement of outside air temperature is essential for safe and efficient aircraft operations. Flying in icing conditions can be dangerous. Ice can form quickly, especially in clouds, and cause serious issues: loss of lift, higher drag, extra weight, and even jamming of control surfaces. Ice shedding from propellers can damage the airframe, and ice entering turbine engines can cause power loss or flameout. In piston engines, carburetor icing is also a common cause of failure. Temperature directly affects air density, which in turn impacts aircraft performance, engine power, and readings of altitude and speed. But measuring outside air temperature is not as straightforward as it sounds. As the aircraft moves through the air, heating effects occur: frictional or kinetic heating, caused by the rubbing of air molecules against the aircraft's skin, and compressional or adiabatic heating, caused by the air being squeezed and compressed at high speeds. Both make the local air warmer than the true outside air. What we really need to know is the true outside air temperature, OAT, because that is the value used for performance calculations, flight planning, and safe engine operation. Even a small error in OAT can lead to incorrect takeoff distances, wrong climb performance predictions, and unreliable fuel planning. In this lesson, we will first look at the basic types of air temperature thermometers and their operating principles. Then we'll examine a total air temperature (TAT) probe used in modern high-speed aircraft. Finally, we'll discuss the common errors these instruments are prone to. Air temperature thermometers fall into two main types: direct reading and remote reading. Let's begin with the direct reading thermometer. A simple example is the bimetallic thermometer. It works on the principle that two metals with different expansion rates will bend when heated. When bonded together as a strip, the metal with greater expansion bends more, causing the strip to curve. The amount of bending is proportional to the temperature. Commonly, the metals used are invar, a steel alloy with very low expansion, and brass, which expands much more. If this bimetallic strip is shaped into a coil or helix and one end is fixed, any temperature change makes the helix rotate. This rotation can drive a pointer around a calibrated dial, giving a temperature reading. Although simple and effective, these direct reading thermometers do have errors, which we will look at later. Still, they are adequate for low-speed aircraft, where high precision is not critical. Modern TAT probes, however, are designed to correct for heating errors and provide accurate values even at jet speeds, making them essential for today's airliners and high-performance aircraft. It is often desirable to have temperature information in an electrical form so that it can be fed to other instruments and systems. Remote temperature gauges work on the principle that the electrical resistance of certain materials changes with a change in temperature. Measurement of electrical resistance will therefore be a measurement of temperature. To measure electrical resistance, a resistance circuit is employed, commonly known as a Wheatstone bridge. We can see here a diagrammatic illustration of a Wheatstone bridge circuit. In basic form, the circuit consists of a power source and four resistors labeled R1, R2, R3, and R4 in our diagram. For a given voltage input, the current flowing through the resistors will depend on the resistances. If the resistances are equal or balanced, the current flow in the circuit will be zero. If one of the resistor is exposed to the outside air as temperature changes, so will the resistance. This will cause an imbalance in the circuit, and a current will flow, which will be proportional to the temperature change. The change in resistance is consequently a measurement of temperature change and can be calibrated. This is an accurate system which can detect even small changes in temperature, and as the system works on the principle of balancing resistances, any fluctuation in the circuit voltage will not affect the accuracy of the system. Let us now look at a typical total air temperature probe of the type used on a modern high-speed aircraft. The probe is usually constructed from nickel-plated beryllium copper, which provides good thermal conductivity and strength. This type of probe consists of an air intake mounted at right angles to a small hollow strut or casing. Inside the casing is a pure platinum wire resistance sensor. Platinum is used because it has a very high rate of conductivity and gives a rapid response to temperature change. Platinum also has a linear resistance change to temperature change relationship, which makes it ideal for temperature measurement. The probe is fixed to the fuselage in a location which minimizes any boundary layer effect. Usually, the front fuselage boundary layer effect is discussed in detail within aerodynamic courses on principles of flight. Here we can see a diagrammatic cross-section of a total air temperature probe. Let us look at how it works. It can be seen that some of the air entering the probe is turned at right angles to pass over the sensing element. This is to separate air to be sensed from any water or solid particles present. Flow separation is achieved because water or solid particles have sufficient kinetic energy to pass directly through air intake and exit the bleed holes. Bleed holes in intake casing allow the higher pressure air escaping from within the intake casing to draw off boundary layer air. An integral heating element prevents the formation of ice. The effect of the heating element on the temperature sensed is small and is not significant. It is also necessary to measure air temperature on the ground. A factor affecting takeoff distance and the takeoff power required is temperature. A reduced power takeoff may therefore be possible, and this is a valuable operational consideration. Without forward movement of the aircraft, air within the sensor casing can stagnate. Stagnated air could give a false indication of the outside air temperature. To re-establish an outside airflow within the probe, an air-to-air ejector or aspirator is used. The principle we can see in operation here is that pressurized bleed air is being drawn from a compressor stage of a running engine or auxiliary power unit and is being fed through the aspirator. This creates a negative pressure differential within the sensor casing, which draws fresh outside air past the sensor element. Finally, in this lesson, we will look at the errors which air temperature gauges are subject to. The first is instrument error. This occurs in the manufacturing process, and unfortunately, manufacturing imperfections are difficult to avoid. The second error is environmental error. This error can occur as a result of solar heating of the temperature sensor. Direct reading thermometers, in particular, can be vulnerable to this type of error. Solar heating can be reduced by shading, which happens in a remote detector. Icing is also an environmental error. And thirdly, we have heating error. We will recall from earlier in the lesson that the movement of the aircraft through the air will cause the air temperature to rise in the immediate vicinity of the aircraft. The rise in temperature is caused by friction or air compression as the aircraft moves through the air, and it accounts for by far the greatest error in high-speed aircraft. Low-speed aircraft are less affected by friction or air compression, and are therefore less vulnerable to this type of error. In this lesson, we have considered why accurate air temperature measurement is necessary and the problems associated with air temperature measurement. We should also now be familiar with the principles of operation involved in a direct reading thermometer, a remote reading thermometer, a total air temperature probe, and an aspirated total air temperature probe. This ends our consideration of air temperature sensors. Part 2 of air temperature measurement will take us through the relationship between temperature and speed and define static air temperature, total air temperature, and RAM air temperature. It will also look at methods of air temperature correction. A summary of the main points of the lesson follows. Temperature affects aircraft performance. Ice can build up quickly, especially in cloud. Ice buildup can cause loss of lift and an increase in drag and weight. Temperature affects air density, which affects engine power and the measurement of altitude and speed. Kinetic and adiabatic heating will give a false indication of the true outside air temperature. The two basic types of air temperature thermometers are the direct reading and the remote reading thermometer. The bimetallic thermometer works on the principle of two metals bonded together with different coefficients of expansion will expand at different rates. The two metals often used in the bimetallic thermometer are interlaminar and brass. A remote reading thermometer works on a Wheatstone bridge principle. The total air temperature probe is usually constructed from nickel PLD beryllium copper. In the total air temperature probe, the sensing element is usually made of pure platinum. The total air temperature probe is fixed to the aircraft in a location which minimizes the boundary layer effect. In the total air temperature probe, an integral heating element prevents the formation of ice. An aspirated total air temperature probe uses bleed air to create an ambient airflow through the probe while the aircraft is stationary. Air temperature gauges are subject to instrument error, environmental error, and heating error. If you enjoyed learning with us, don't forget to like this video, share it with your fellow aviators, and drop a comment with your thoughts or questions. Your support helps StudyKwik keep bringing you clear, exam-focused aviation lessons.